Hello again everyone, welcome back to ptet.chemistry channel. So I've just done quite a bit of qualitative analysis this morning, and in this video I just want to show you a couple of reversible changes, a couple of equilibrium that involve transition metal color changes, and we can use this as the basis of discussion for Le Chatelier principle or under any sort of chemical equilibria, whether it's for O-level, IGCSE or A-levels. They all learn the same idea about equilibria and how the equilibrium will respond to the changes. Here we're doing solution chemistry. This is called potassium dichromate 6. So it's a dichromate Cr2O7 2- and a K+. So you need 2 K+ and 1 Cr2O7 2- to give you the overall formula of K2Cr2O7. This is an orange color solid, and it's also an orange color solution. And what it does is it is carcinogenic, and that's why it's been taken out of the O-level or the IGCSE curriculum. It used to be in the curriculum as a very popular oxidizing agent. Now you only learn KMnO4 as your common oxidizing agents in O-level and IGCSE. But K2Cr2O7 or Na2Cr2O7, the dichromate 6, because the chromium is +6 oxidation state, very powerful oxidizing agent, and yeah, it's commonly asked in A-levels. It is something which is not taken out from the A-level syllabus at all. Although it's been taken out of the qualitative analysis, the practical bit, it has not been taken out from the theory bit. This is potassium chromate. So chromate is the important ion here. This is CrO4 2-, CrO4 2- with a K+, so it's 2 K+, well, meaning 2 of the K+ cation and 1 of the CrO4 2-. This is yellow in color. This is also chromium +6, just like the dichromate, chromium +6. And you can get an equilibrium between the two actually. Okay, so that's what I'm going to show you. I actually forgot what is what already. I think it's CrO4 2- that goes to Cr2O7 2-. Yeah, okay, I think I got this right. Okay. So this is the yellow color chromate, yellow color Cr2O4 2-. The cation is just there as a counter cation. Okay, Cr2O4 2-, yellow in color, yellow in solution, beautiful yellow solution. Cr2O4 2- aqueous is yellow in solution. Cr2O4 2-, yellow in solution. Okay, and all it takes is a little bit of acid. I'm not too sure how strong the acid it is, but I'm just going to add dilute nitric acid. You could use dilute sulfuric acid or dilute hydrochloric acid. The important thing here is acid. The equilibrium involved H+. I don't know if it will work. Let's see. Oh, there it is. Okay, you see what happened? The yellow color has gone to orange. The yellow color has gone to orange because the Cr2O4 2- is being converted to Cr2O7 2- in this non-redox. It's not a redox reaction, it's an acid-base reaction. There's no change in oxidation number because remember I said earlier, Cr2O4 2-, Cr2O4 2-, it is a chromium +6. It's called chromate (Vi) to represent the +6 oxidation state of chromium. This is Cr2O7 2-. This is called dichromate 6 or dichromate (Vi) to represent the chromium +6 cations. Okay, so the yellow color could go to orange color, and you could write equation for it, which I'll try and show on a picture. And this is the result of adding H+ to the yellow color potassium chromate. The question is, what happens if I take away? What happens if I take away the H+? So if I have a little bit of this orange color solution, so this is the dichromate now because it's gone orangey. Orangey supposed to be the dichromate. Maybe I could make up a solution of the dichromate. That would be better, isn't it? Okay. Yep, this is clean. So I'll make up a solution of the dichromate. So this was the orange color solution. This is the one that's been taken out of the O-level syllabus because of how carcinogenic it is. This is the orange color potassium dichromate. So I made it up from this thing. Okay. Whereas this one was obtained by adding H plus to the yellow color chromate 6. This is now the dichromate on its own. The question is, how can I make the dichromate goes back to the yellow color? If I add more acid to it, it's not going to work, because that's why we have acidified dichromate 6, because it remains as orange color solution. Acidified dichromate 6 is also orange in solution. Okay. So what I'm going to do is I'll divide it into two. Okay, so this is from the dichromate 6. First of all, I'll just add acid to it. Dilute nitrate or dilute hydrochloric or dilute sulfuric, doesn't matter. You see if there's any color change or not. There will be no color change, it will remain orange, because the equilibrium shown basically it only reacts, the H plus from acid only reacts with the CrO42 minus, which is the chromate 6, the yellow color one. So how in the world can I go from the orange color dichromate 6 going back to the yellow color? Well, if I can't add acid to it, but there's something that can take away the acid, something that can react with the H plus, something that can take away the acid, and there's something you learn as hydroxide. I could add sodium hydroxide, I could add ammonia, I think, but I know sodium hydroxide would definitely work. So, clean dropping pipette. So this is my dichromate 6, orange in color. If I add a lot of sodium hydroxide, you notice that the yellow color has gone, the orange color of dichromate 6 has gone yellow, because looking at the equilibrium, even though there's no OH minus in the equilibrium, OH minus react with acid, OH minus take away the H plus, therefore H plus concentration decreases, so the equilibrium shift to the side. In order to increase the concentration of H plus, it shift to that side, and therefore it will go back to that side of the chromium 6 plus, which is the yellow color chromate. Of course, this yellow color now, if I add more acid to it, oh no, my acid is running out. Okay, never mind. I add some more acid to this yellow color solution, so it's not magic. But as you can see, the yellow color has gone back to orange. So this is a beautiful observation of these reversible changes involving equilibrium. Okay, so a lot of it comes down to actually seeing it, and then you can discuss the equilibrium not just in classroom among teachers, but also it's a very good exercise for students to do, because as students or as learners, when you see these color changes, you understand equilibrium, you understand about, because you could see, right, so you understand about applying Le-Chatelier principle. Le-Chatelier principle says when you have a system in equilibrium, when you introduce a change to the system or the equilibrium will try to oppose the change. Alright, it will try to resist the change, oppose the change. Okay, so there are a couple of other examples which I will append my raw videos from other bits and pieces of tutorials, and hopefully they will make more sense. Okay, so thank you for watching. Thank you for watching these tutorial videos. I've appended some other videos from my other tutorials on qualitative analysis that kind of cover the overall theme of this particular tutorial, which is on reversible changes, Le-Chatelier principle based on color changes that you could see. Alright, so again, thank you for watching, thank you for supporting the channel, and thank you for sharing the channel with all your friends, your chat group, your study group, your juniors or your seniors from school, not just those who are doing A-level chemistry, but those who are doing O-level or IGCSE chemistry, and the various topical playlists on the channel means that they cater to people who are not just preparing for exam, but also the beginning learners at whatever stages of their curriculum. Topical playlists enable them to revise the syllabus based on what each topic intends for them to be able to achieve the learning objective as stipulated by Cambridge. Okay, so follow me at ptet.chemistry. There is ptet.chemistry on Facebook, Instagram, and Twitter if you use this social media platform, or if you plan to return to them after you finish exams. Alright, thank you for watching again, and I'll see you in the next tutorial video. I think I'll just show you what happened when I add just one tiny drop into it. So you'll be given dilute, right? You'll be given dilute. Not really, no. You'll be given a dilute ammonia for QA. So this is essentially the initial precipitate that you will get, because the ammonia is acting as a weak base. It gives you the hydroxide ion that will precipitate out the copper 2 plus as copper 2 hydroxide, pale blue precipitate to begin with. And then in excess ammonia, it doesn't need to be concentrated ammonia. The dilute ammonia that you have will bring the pale blue precipitate to this deep blue solution. So this other pale blue precipitate, copper 2 hydroxide, is just the ammonia acting as a base, but then ammonia can also act as a ligand, and they will eventually replace the water molecule, and then you get copper 2 plus with 4 NH3 and also 2 H2O remain. It's still a 2 plus charge complex, and this is a deep blue or dark blue solution. Very distinctive color to indicate the presence of the copper 2 plus. So what happened with this complex is that it's got 4 ammonia and 2 H2O molecule with a 2 plus charge. I could drive it towards this green color solution. There is copper with 4 chloride around it. So what I'll show you now is just by adding hydrochloric acid, concentrated hydrochloric acid to this. This will be my source of chloride. So this is the blue color solution. So I'm adding concentrated HCl. Oops. I think I'm accidentally pouring some of this outside. So I need to be careful. I probably had too much of it in there. That is not going to go anywhere at all. Okay, so slowly you could see that the solution has gone, the deep blue solution has gone green. Initially it took a bit of time for it to start because the HCl is the acid. The acid will try and remove the NH3 as the base because of the neutralization reaction. So the HCl will react with the NH3 in the neutralization reaction to begin with. But after some time, when I add more and more concentrated hydrochloric acid, the Cl minus, what it does is it will replace the NH3 molecule as a ligand. So it's a ligand substitution reaction and results in this green color solution, which is essentially copper 2 plus surrounded by 4 Cl minus ligand. Okay, so this is just an example of a ligand substitution reaction, and it's all reversible. So I'm using concentrated start, that's why there are fumes all over. By right, it should have a ventilator that's working, so it should all suck the gas properly. So what happened to this reversible reaction is this is the green color thing. If I add more water to it, water can compete as a ligand, and as you could see, it's a very pale blue solution now because it's gone back to the copper 2 plus surrounded by 6 H2O molecule. Okay, just like this one was in the ammonia. Oops, hang on. I need to be picking this up properly. So this was in ammonia a little bit just now. So I'm going to add a bit more ammonia to get the dark blue complex. Okay, so that is nice and happy, dark blue complex, but then I'm going to add a lot more water. And in a very large amount of water, if I remove some of these, if I remove some of that solution and then keep on adding water, this solution will eventually, because I'm introducing more and more H2O to it, the deep blue solution will go back to the pale blue solution because it drives back the equilibrium where the water molecule replaces the NH3 molecule, and I should get the pale blue solution. So it's still pretty concentrated with the ammonia complex. So it should pretty much go back to this color later on. Okay, I'll see if I can actually put a lot more water and see if I can get it. Yeah, it kind of goes really pale blue solution now. Okay, so that's it for copper 2 plus chemistry. We'll probably stop here for the time being, so it's not very comfortable with the mask and all these dangerous toxic fumes, especially with in this non-ventilator fume hood. Okay, so just to further drive home the message that we can get these compounds called copper 2 chloride dihydrate. So this is copper 2 chloride. It's kind of like blue greenish in color, but I'll just show you what happened when you dissolve it in solution. So you should get a clean spatula. Yep, that's reasonably clean. So this is copper 2 chloride. Copper 2 chloride. Okay. Oof, a bit disgusting there. It's kind of like greeny bluish in solution. And once it is in solution, you have a lot of the blue, pale blue solution instead of the greeny color solution that we saw earlier, because in the presence of distilled water, deionized water, I've just introduced a lot of water molecules, and these water molecules just basically surround the copper 2 plus. To get back the green color species, what you do is you can add concentrated hydrochloric acid to this. They will compete with the H2O molecules, and they will replace the H2O molecules to give you back the tetrahedral complex, which is the Cu2 plus and 4Cl minus. They will be greenish in color. Okay, so as a solid, this copper 2 chloride dihydrate. The dihydrate is a water crystallization, so it's copper 2 chloride, so it looks a bit greenish. As you could see, it's a bit greenish there because in a small amount of water, if I have, okay, now I can see where it comes from already. I'll just add a very small amount of water and see what the color is. How you can see the color? So this is the same compound. In the very small amount of water, it is green. Okay, just like when we added concentrated hydrochloric acid to the pale blue solution containing the copper 2 plus with a lot of H2O just now. But if I dissolve this in a lot of water, so if I add a lot more water to this is CuCl4 2 minus. If I add a lot more water to this is the idea of reversible equilibrium. These are all to do with ligand substitution. A lot more H2O molecules means they compete. In fact, they oversaturate the Cl minus ligands, so they will win over it, and therefore you compete with that equilibrium. You shift to the other side of the equilibrium. With the increase in water concentration, you get this copper 2 plus with 6H2O around the copper 2 plus, giving you this pale blue solution of copper 2 hexaaqua complex. Alright, so that's it for copper 2 chemistry. So we're ready to start this qualitative analysis. So I have a bottle of distilled water or deionized water. I will dissolve this cobalt 2 chloride hexahydrate in water, and what we'll get is a pink color solution. So they're not very soluble because they are solid, so I might have to swirl it around a little bit harder. They're slowly dissolving. So it looks like almost all of them has gone. Okay, I have a little bit more of that cobalt chloride that I poured just now. I was supposed to show you a cutback to a separate tutorial video which I had taken another time. That was to do with the heating up the hydrated cobalt 2 chloride, and they're supposed to show the pink color solid going to blue, and you have seen that in the other section of the tutorial video. So this is cobalt
2 plus surrounded by 6 water molecules. A-level students will know that this is a cobalt 2 complex. It's a hexa-aqua complex. So pink color solution. I will divide it into separate portion. First portion here, second portion here. I should use another different tube. Okay, so first of all, I want to add a little bit of sodium hydroxide. So sodium hydroxide is a base. What happened when I add sodium hydroxide to this is that we will see you get a blue color precipitate. So I don't know, against the background, this background is probably as good enough. So you do get a blue color precipitate in contact with sodium hydroxide. So there is cobalt 2 hydroxide. It's a precipitation reaction. And of course, what happens when you add the cobalt, well, when you add the sodium hydroxide in excess, the blue color become more apparent. So there's the blue color become more apparent, and obviously you could see that the precipitate remains insoluble in excess sodium hydroxide. I've added quite a lot of sodium hydroxide now. This is cobalt 2 hydroxide. It precipitates out as a blue colored solid. Sorry about the camera angle. Precipitate as a blue colored solid. Alright, so that is insoluble in excess sodium hydroxide, NaOH. Now I'm going to try and add a little bit of ammonia to it. Ammonia, aqueous ammonia, NH3. So I will see what happened here. We get a similarly colored precipitate, but they look slightly different. This is a bit a darker shade of blue, a different shade of blue, but it's still a precipitate. As you can see, some of them get deposited on the side of the tube. I may need to add a little bit more because I think I had quite a lot of the cobalt 2 plus salt dissolved in water just now. So perhaps the color will become clearer when I add a bit more. And it does become clearer when I add a bit more ammonia. And the precipitate remains insoluble in excess ammonia as well. So as you can see, this was in ammonia. It's kind of like a different shade of blue. This was in excess NaOH. This is what ChemGuide had mentioned on the website. It started out as a blue thing, but they turned out to be a little bit of pink color style on top. But ideally speaking, we always consider the cobalt 2 hydroxide to be a blue colored solid that remains, in excess NaOH. And this is the a different shade of blue. We call this blue as well, blue precipitate. But as you can see, they're different color kind of blue that remain insoluble in excess NH3. Now this is still the cobalt with just water in it. What I'm going to do is, I think the last time I tried this, I had a bit of acid which was no longer fuming or concentrated. What I have here is a hydrochloric acid. So hydrochloric acid, concentrated hydrochloric acid is colorless. I don't want to be breathing it in, so I will add a little bit of it to this pink color solution. Let me go and grab a test tube holder. And I'm back with a test tube holder because we don't want to be spilling the corrosive acid on our hands. Alright, so adding a little bit of concentrated hydrochloric acid to this pink color solution. The concentrated hydrochloric acid has a lot of chloride, Cl-, that can help to replace the H2O molecules, and you will see what happened hopefully. Okay, I hope the color changes is quite clear. It's very distinctive, isn't it? Okay, so it's gone kind of like blue color, very nice blue color there. So it's gone from pink, which is the hydrated complex, to this very nice blue colored complex, which is basically cobalt with cobalt 2 plus with 4 Cl minus around it. So now it's Cl4 2 minus, and to counter you also have a Cl2 plus, and of course you have a Cl2 plus and Cl4 2 minus. The stoichiometry is still correct, it's still cobalt chloride. Okay, So ideally speaking, when you have heated the hydrated cobalt 2 chloride, you get anhydrous cobalt 2 chloride, which is kind of like blue, purple, or blue in color. Okay, this is just a deeper shade of blue. So all of them looks blue, but it's a different shade of blue. This is the color of cobalt with 4 chloride around the cobalt 2 plus, therefore CO2 plus and 4Cl minus, giving you COCl42 minus. Alright, so that was just on their own. I added the ligands, the substance itself,